So, welcome to the next lecture that is on wave particle duality in quantum mechanics series. Today, we will discuss the wave particle duality Davission Germer experiment, that is the proof of the dual nature of light, that is experimental verification of dual nature of light. So, let us discuss this. What is wave particle duality? Wave particle duality means while studying the interference, diffraction, polarization, we treat light as a wave. And while explaining the concept of photoelectric effect, Compton effect, we treat it as a photon, that is particle. That means the same light is like a wave and like a particle. So this is called the dual nature of light. So let us discuss this. So matter waves, DeBroglie hypothesis put forward in 1924, and Lewis DeBroglie, he was awarded a Nobel Prize in 1929 for this prediction of wave nature of light. So what he says, the total energy of matter related to frequency nu is given by E is equal to h nu according to Planck's theory, and the momentum of matter related to wavelength lambda is 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 given by p is equal to h upon lambda. So p is the property of the momentum which is related with the wavelength, that is h upon lambda. So lambda is a property of wave, p is the property of matter or say momentum. So these are related, and this is derived by this Lewis de Broglie. Let us derive this expression. Let us derive this relation between momentum and the wavelength of that light. So this prediction, that is the particle and wave, these are associated. That means every particle, every matter is associated with wave, that is wavelength lambda. And this prediction was experimentally verified by Davission and Germer in 1927. We are going to discuss this experiment in detail. Okay, so let us have the proof of P is equal to h upon lambda. So here wave particle duality, de Broglie wavelength we can say. So energy of photon is equal to E equal to h nu hc upon lambda, and relativistic energy is given by E is equal to p square c square plus m0 square c to the power 4 to the power half. And for rest mass of photon is equal to 0, photon mass is equal to 0, photon is massless, so energy becomes is equal to Pc only. So if you compare this equation number 1 and equation number 2, we'll have this Pc is equal to hc upon lambda, and therefore we say P is equal to h upon lambda and lambda is equal to h upon P. So this is called the de Broglie wavelength. So de Broglie wavelength is nothing but the lambda wavelength associated with particle moving with, or say having momentum, say P. So let us discuss the Davisson and Germer experiment in 1927. So this is the simple arrangement. So here is there is a filament where the power supply is given to the filament and electron is emitted. The kinetic energy of electron emitted is directly proportional to the potential difference applied. This emitted electron beam is made to fall on the nickel crystal, and after nickel crystal, after diffracting from the nickel crystal, it is diffracted in different directions, but it can be the scattered beam of electrons can be detected by this detector in every angle. In every angle it is detected. So scattered beam is detected by this detector at particular angle, say theta. So this is the simple arrangement. The electron beam, high energy electron beam is made to incident on the nickel crystal, and after scattering from this nickel crystal, its intensity is detected by this detector. So let us have some experimental observations. So this is the graph between collector current versus the kinetic energy of electron. It is like this. The nature of graph is like this, and it has a peak at theta is equal to 50 degree. That is at an angle of scattering 50 degree, it is having maximum collector current. Okay, and at an angle at a kinetic energy, or say that kinetic energy is in terms of the voltage, and voltage is is about say 54 volt. And if you plot the graph between collector current versus the angle of scattering, then at an angle, oh sorry, at the potential difference 54 volt, the graph is like this. It is having peak at 50 degree. So these are the two graphs can explain that there is a maximum peak at an angle 50 degree and at voltage 54 volt. So these are the experimental arrangement and experimental observations. So let us treat this electron beam as a beam of particle, and we treat this electron beam as a wave. Then see what happens. If you treat electron as a wave, if you apply the Bragg's equation, then 2d sine theta is equal to L lambda. And if you put the value of 2d for nickel, the interplanar spacing for nickel, 2d is 2.15 angstrom, and theta is equal to 50 degree, n is equal to first order, n is equal to 1. So therefore, if you calculate this, lambda is equal to 1.65 angstrom. So if you treat electron as a wave, then lambda comes out to be 1.65 because we are using the Bragg's equation. Now, if you treat electron as a particle, kinetic energy of particle or say kinetic energy of electron is p square upon 2m, and this kinetic energy is provided by this potential difference, and therefore we say that potential difference, if it is energy is equal to E into V is the potential difference. And if you replace that in the formula, that is if you put this value in this equation, lambda is equal to h upon p, and p is equal to square root of twice me, and if you put these values, these are constant, h upon twice me is constant, and its value comes out to be 12.24 upon square root of v. And if you put the value of v, that is say 54 volt, then you will get lambda as 1.67. So by treating electron as a particle, the lambda comes out to be 1.67, and by treating electron as a wave, the lambda comes out to be 1.665. These two values are very similar. Okay, that means our prediction that electron is acting as a wave and electron is acting also as a particle is correct. So this is the experimental verification of Davission and Germer experiment to predict that the matter or say the waves are associated with matter. So here we can now see the concept of the wave packet. Now when the waves interfere with each other, okay, then the resultant wave is like this. Simply we can say the group of waves come together to have a wave packet. So as I said, a continuous distribution of wavelength can produce a localized wave packet. We can say localized wave packet. So this is the these are the waves, and finally you are getting this wave packet. Okay, the result is this resultant wave. We can say this is called the wave packet. So each different wavelength represents a different values of momentum according to DeBroglie relation. So each wave here is having different wavelength and therefore different momentum. So superposition of different wavelengths is necessary to localize the position. A wider spread of wavelength contributes to smaller delta x. So if this is wider, then this will be small. Okay. So delta x, which is the length of this wave or say wave packet, we can say it is delta x. One can say it is the small change in displacement, we can say. So here one can represent the wavelength. This is a lambda m, which is peak wavelength, and this is a delta lambda. Okay, so delta lambda and delta x, they are interrelated, and we have the DeBroglie equation P is equal to h upon lambda. So this is the wave equation. This is the phase velocity. Phase velocity is equal to lambda upon k. And if you see the superposition of two waves, y is equal to y1 plus y2. And if you apply the simple relation, trigonometric relation, and apply this, you will get the resultant wave like this. So this is the resultant wave. Nature of resultant wave is same as the uh, combining waves are say y1 and y2. And here the amplitude of wave is given by like this. And the here, so this is the group of waves. So after combining two waves we are getting this equation, and this can be treated as a group of waves, and it should have the group velocity, and that group velocity is given by d omega by dk. So single wave will have the phase velocity, and group of wave will have the group velocity. So let us derive the relation between phase velocity and group velocity. So here we have the expression phase velocity is equal to omega upon k and group velocity is equal to d omega upon dk. So let us proceed further. Omega is equal to Vp into k from this equation. So let us differentiate this. We'll get this equation. So d omega by dk is equal to Vp plus k into dVp by dk. So d omega by dk is nothing but the group velocity, and if you replace this d omega dvp by dk like this by using this equation, we are getting this equation, and therefore vp is equal to, or say d omega by dk, which is nothing but group velocity is equal to vp minus d lambda into dvp by d lambda. Dvp by d lambda means there is a change of rate of change of phase velocity with respect to lambda. So for the dispersive medium where Vp depends upon lambda, Vp changes with lambda, then in that case Vg is less than Vp. But for the non-dispersive medium, Vp is independent of lambda, therefore Vg is equal to. So we have the simple illustrative problem, a 10-gram bullet moving with 1000 meter per second. So we want to calculate the wave associated with that bullet. The wavelength comes out to be like this, which is very, very small, cannot be detected. So this is how one cannot experience, or say one cannot detect the wave associated with the 10-gram bullet moving with 1000 meter per second. So larger particles also have waves connected with it, but we cannot detect, being a wavelength is very small. Okay, thank you so much. We will discuss more in the next lecture.